I hope you all remember the ground rules, and I am hoping that we're going to have a lot of information on HIV today. Group leader, you can start with the scenario repetition first, and then on to that.
Okay. A 29-year-old male, Salim, visits his GP complaining of cough and hemoptysis. He is a non-smoker. He has also noticed some weight loss. On examination, he is anorexic and clammy with a raised temperature. Blood tests show a reduced white cell count amongst other abnormalities. Past medical history includes a blood transfusion following a road traffic accident 2 years ago. He is married to Lubna, who is 24-year-old with a 1-year-old baby. The GP ordered an HIV test that came back HIV positive. How would you approach the patient in light of the disease pathophysiology, signs and symptoms, complications, treatment, and implicit social issues? Okay, let's start with the first objective, that is, what is the pathogenesis of HIV, and 476.
Yes, I am adding together. I would like to keep it in the top, starting with the structure. The HIV virus is basically an RNA virus. It has two identical strands of RNA with reverse transcriptase enzyme. Virus is encoded by a nucleic acid, which is further encoded by matrix protein, and then a lipid bilayer containing.
Would you like to draw this on the board?
Yes. This is basically the two strands of DNA, sorry, RNA. This is the reverse transcriptase enzyme, and there is another enzyme that is called the virus protease. There is a nucleic acid code, and then there is another code of matrix protein. And then there is a lipid bilayer envelope which contains proteins such as the G120 and the GP41. This is the basic structure of the virus. And
Did you all get that?
Yeah.
Lubna, can you repeat?
There is double-stranded RNA, the long and reverse transcriptase, and outside there is a nucleic acid, and out of which there is the matrix protein, or uske baad, and then there is the outermost code which is which are receptors, that is GP120.
The reverse transcriptase enzyme is inactive initially. This is activated by the viral protease enzyme. This has three activities. One, RNA dependent DNA polymerase. The other is RNA DNA polymerase. What happens is basically, supposing this black is the RNA, the first enzyme will produce a complementary DNA. This is grouped together. The second one breaks these groups, and the third one produces a double-stranded DNA structure. There are some structures in the RNA. These are called untranslated portions. There are both the 5' and 3'. These are transcribed into the double-stranded DNA's long terminal repeats. Now what happens is, if this is the DNA of the host cell, this thing minus these long terminal repeats, which form a circular DNA, this double strand is incorporated into the DNA, and this is called a provirus.
Into the DNA of the host?
Into the DNA of the host. This is called a provirus. And inside this DNA, which got a lot of things, including genes known as GAG. These are a few of the genes. GAG.
G.
This pole codes for the enzymes. ENV codes for the envelope, particularly these GP 120 and 41.
GP stands for?
Glycoprotein. And the tag for the viral capsid. Which is this one, nucleic acid.
Okay, are you guys getting that? Did you guys understand the whole process of replication? Hamza, did you get that? What did you get?
Can you repeat that structure?
Yeah, I'll start again. This is basically the reverse transcriptase enzyme. This is inactive initially.
I think you stand on that side now because this side
Sorry.
wants to see.
This is the reverse transcriptase enzyme which I have shown by this. This is basically inactive. This is what I've tried to show over here. The viral protease, this enzyme here, this cleaves this, a part of this, and this is converted into the active reverse transcriptase enzyme. Now this has three fundamental activities. RNA-dependent DNA polymerase, that is, it uses the template to DNA, which is called the complementary DNA.
It is going to look at one template, it is going to copy it into a DNA. So you know the difference between DNA and RNA. What is the difference?
This DNA and this RNA, they're actually joined together. This is the enzyme. This is the function of the second enzyme. It breaks these so that it is free for the enzyme to come in place and produce a complementary double-stranded DNA. There are, at the end of the RNA, there are some, both at 3' and the 5' untranslated portions which do not get translated, converted into long and incorporated into the bromide. This portion goes in to the bromide. The terminal repeater stuff remains out in the circular DNA, in the form of the circle. This is the provirus. Okay? This is the provirus. Inside these, the incorporated DNA, a lot of genes, a lot of DNA, part of which encodes for the envelope, which is and particularly in the envelope, this is GP41 and GP120. The pole part encodes for the enzymes. This enzyme being the most important among others, and the GAG codes for the nucleic acid. This is the basic replication of the enzyme. Now I'd like to move on to entry of the virus. Basically, the virus replicates inside CD4 positive receptors. These include lymphocytes, macrophages, and these three, they have a CCR5 receptor, and this one has a CXCR4 receptor. The C represents cysteine, an amino acid, and it represents any amino acids which are between residues. And these are the two receptors. Four receptors. What happens in the virus by means of this GP120? This is the receptor, and this is the GP120. When it comes here, this is the lipid bilayer. And there is this 7 transmembrane chain that goes inside. This brings about a conformational change, and this is the rest structure of the virus. This brings about a conformational change which allows the inner part of this envelope to become a part of the host cell membrane, and the inner part, this goes in. See? That's what goes in. Once it's inside, it starts replicating like before, and that's where it replicates. Now, lymphocytes, macrophages, these are cells that are there in the immune system. They are continuously active, they're continuously dividing. So that is why every time the lymphocyte or the macrophages or any of these cells divide, I'll tell you one thing, 99% of the virus load comes from lymphocytes alone, because active when there is an infection. Come from this.